Welcome! In this video, we'll be exploring two key learning objectives in AP Precalculus. First, we will learn how to construct and compare different types of function models, like linear, quadratic, and exponential, to fit a given set of data. Second, we will learn how to validate these models using a tool called a residual plot. This will help us determine if a model is appropriate for the data and the real-world context. By the end of this lesson, you will be able to take a data set and confidently choose and then justify your choice of the best function to describe it. Let's begin with our first objective, constructing and comparing models. When we look at a set of data, how can we determine the best type of function to represent it? We can analyze the rates of change in the data. There are three main function types to consider. First, a linear function. A linear model is appropriate when a dataset has a constant rate of change. This means that for every step you take in x, the y value changes by the same amount. Next, a quadratic function. A quadratic model is appropriate for data with a constant second difference. This is the difference of the differences. Finally, an exponential function. An exponential model is best when the data has constant ratios. This means that each y value is a constant multiple of the previous one. So, to recap, we examine the differences to find a constant rate for linear models, second differences for quadratic models, and ratios for exponential models. Let's put this into practice with a numerical example. Consider the following data table. We have x values from 0 to 4 and corresponding y values. To determine the model, let's find the differences. The difference between 4 and 2 is 2. The difference between 6 and 4 is 2. And so on. We can see that the first differences are all 2. Since the first difference is constant, this dataset is perfectly modeled by a linear function. In this next example, the first differences are 2, 4, 6, and 8. They are not constant, so it's not linear. Let's find the second differences. The difference between 4 and 2 is 2, the difference between 6 and 4 is 2, and the difference between 8 and 6 is also 2. Because the second differences are constant, this dataset is perfectly modeled by a quadratic function. Analyzing these patterns is the first step. But what if the rates of change aren't perfectly constant? In the real world, data is rarely perfect. Let's look at another method. This method relies on interpreting the shape of the data when plotted on a graph. Here is a graph of a dataset. Notice the points appear to follow a straight line. This suggests a linear model is a good fit. We are looking for a general trend. It doesn't have to be a perfect straight line. If the points cluster around a straight line, we consider a linear model. In this next example, the points seem to form part of a parabola. This indicates a quadratic model is likely the best choice. And here, we see the points getting farther apart as x increases, showing a clear upward curve. This is characteristic of exponential growth. So, by visualizing the data, we can make an educated guess about the underlying function. Once we've identified a possible function type, we can use technology, like a graphing calculator or software, to find the regression equation. This process, called regression, finds the specific line, parabola, or curve that best fits our data. For our first example, let's say the data suggests a linear model. A linear regression would give us an equation in the form y equals ax plus b. That represents the line of best fit. Our calculator might tell us that the best linear model for our data is y equals 2.05x plus 1.98. This is our predicted model. It's important to remember that these are just potential models. Our next step is to validate them. This brings us to our second learning objective, validating a model. Finding a regression equation is not enough. We must determine if that model is actually appropriate. The primary tool for this is a residual plot. Let's first define what a residual is. A residual is the difference between an actual y value from our original data and the y value that our regression equation predicts. It's the vertical distance from a data point to the regression line. A positive residual means our model underestimated the actual value. A negative residual means it overestimated. A residual of 0 means the model hit the point exactly. A residual plot is a scatter plot of these residuals against the corresponding x values. It helps us see a pattern in our errors. So, a residual plot shows us how the errors of our model are distributed. It's a powerful way to check if our model is any good. Now, let's learn how to interpret a residual plot to validate a model. A model is considered appropriate if its residual plot shows no clear pattern. This is what we call random scatter. Here is an example of a good residual plot. Look how the points are scattered randomly around the horizontal line at 0. This random scatter tells us that the model's errors are random. It's not systematically under or overestimating values. It fits the data well. Conversely, if the residual plot shows any clear pattern, the model may be inappropriate. A pattern indicates a systemic error. For instance, if the residual plot looks like a parabola, that's a pattern. Or, if it has a megaphone shape, that's also a pattern. If you see a pattern, it means the model is the wrong type. For example, if a linear model produces a parabolic residual plot, you should try a quadratic model instead. The pattern tells you which model to try next. Beyond the statistical validation, we must also consider the context of the problem and the meaning of the errors. This is called error analysis. The impact of an error depends entirely on the situation. An overestimate in one situation might be fine, but in another, it could be catastrophic. For example, consider modeling the dosage of medicine for a patient. A model that consistently overestimates the dosage, giving a positive residual, could be dangerous. Here, a model that minimizes overestimation might be preferred, even if its overall error is slightly higher. The type of error is more important than the magnitude of the error. On the other hand, a model that consistently underestimates demand for a popular product, leading to negative residuals, could be very costly for a company due to lost sales. The key takeaway here is to always consider the consequences of your model's potential errors. The best model is the one that best suits the purpose. So, how do you combine all these concepts to choose the best model for a dataset? Here is a simple, 4-step process. First, explore the data, plot it, and analyze the rates of change to get a feel for what kind of function might be appropriate. Is it linear, quadratic, or exponential? Second, compete models. You should always compare at least 2 plausible models. For example, if you think it's linear, also try a quadratic, since a parabola looks almost linear over a small interval. The process is called competing models for a reason. You're making them go head-to-head. Third, validate using residual plots. Calculate and plot the residuals for each of your competing models. The one with the most random scatter is a strong candidate. Fourth and finally, justify your choice. This is where you explain your reasoning using both the random scatter in the residual plot and the context of the data. Don't just show calculations. Explain what they mean. Let's quickly review what we've learned. Our goal today was to construct, compare, and validate function models. We covered 2 key learning objectives. First, we learned how to construct and compare models by looking at rates of change and graphical shapes. We used technology for regression. Second, we learned to validate models using residual plots. Random scatter is good, a pattern is bad. We saw how to analyze residual plots to justify our choice of model. The key is to look for randomness. If you see a pattern, it tells you the model is wrong. We also discussed the critical importance of context and error analysis, understanding that not all errors are equal. By following this structured approach, you are now well equipped to tackle AP Precalculus problems on competing function models. Good luck! To solidify your understanding, here are some practice prompts you can try on your own. First, take the population data for a local town over the past 20 years, find the best model, linear, quadratic, or exponential, and create a residual plot to validate it. Second, analyze the resale value of a car over the first 5 years. Which model seems most appropriate, and why? Consider the context. What should happen to a car's value over time? These exercises will help you apply the techniques we learned today. Use technology for the calculations, but focus on the reasoning and interpretation. Thank you for joining this lesson on competing function model validation. If you have more questions or need further help, please consult your teacher or textbook. Understanding how to choose and justify a mathematical model is a crucial skill, not just in precalculus, but in many scientific and professional fields. Remember the key takeaway: a random residual plot means a good model. A pattern in the residuals means you need a different model. The ultimate goal is to find the most appropriate model to make the best predictions or decisions for any given situation. You now have the tools to do just that. Finally, let's connect our learning back to the AP Precalculus skills we mentioned at the start. By constructing and comparing models using numerical data and graphs, you are honing your ability to identify information from different representations. This is skill 2. A. You are not just seeing numbers, you're seeing the underlying patterns and understanding the story they tell. And by validating models with residual plots and explaining your choice, you are practicing skill 3. C. Supporting conclusions with logical reasoning and appropriate data. You are building a powerful argument for your model choice. These skills are fundamental to precalculus and will be essential as you move on to more advanced mathematics. You've made great progress today.